Hi, welcome everyone. Welcome to the August office hour. We're doing improvement in self-healing. So what we're going to do is we're going to have Alexey Zatelepin to actually take us to do a deep dive in how to do partitions, what it actually happens during the partitioning rebalancing. So we're going to do that. And so Alexey, can you tell us a little bit about, why do we need partition rebalancing and what is this self-healing all about? When do we need it?
Add a new node instead of it, right? Or you need to scale up your cluster to add some more new nodes. Or like you have a event where like your disks are a bit overflow and you have to, rejiggle your data across the cluster. So it's very important to kind of try to always maintain the cluster in the healthy state, or at least close to the healthy state, where like all nodes are operational, all partitions are replicated fully according to the replication factor that you specified when you created a topic. And basically ensuring that you are far away from this failure boundary that you shouldn't cross. So this is what one of the things that ensures that it's continuous data balancing.
Yeah, I can kind of see that because everything is kind of simple when you start a Kafka or a distributed system where everything's working fine, but like in a couple of days after you have people like writing data or inputting data like crazy, then you start to see that unbalancing of data and where everything are. Or if you happen to have any crash node, then that's when it comes to the truth of like, all right, I need to make sure that everything's working correctly and distributed correctly, right? So that's, yeah, I think that's really great. And you know what? I want to like really ask you, like, because since we have you here, you're the expert. Can you tell us like what is actually happening underneath the hood when we actually kickstart a rebalancing of partition? Can you tell us a little bit about it? And then maybe you can drag things around if you want to on the diagram and let us know what's going on. Or I can do that too, but yeah.
Yeah, I don't know if it's a little or a lot, because I can talk for a long time.
Yeah, but the thing is like, maybe we can start with like, now we have like 3 brokers. Like, how do they know each other? Like, how do they communicate with each other? And then there's a bunch of partitions. So how do they know which partition works and which partition doesn't work? Can you like tell us a little bit about it? And maybe we can start there.
Yeah. So first thing to understand is that we have this global partition map. So it's like it's drawn here on the screen. Like we can see this, that topic A partition 1 is here, and it has a replicate on this node, on this node, and on this node. And the thing is that it is global.
A quick question. So with this map, is this stored like on every broker, or how is it shared? Can you tell us a little bit about it?
Oh yeah, sure. So we have this thing called controller raft partition. So it's like a small system partition that unifies all Redpanda nodes. So every node in the cluster is part of it. And so basically it's like a log of update commands. So we have a command like create a topic, and it gets added to the system partition and gets replicated across all nodes in the cluster. So this means that, so for example, when you create a topic, after this command gets replicated, every broker like updates its internal map, its internal partition map for the partitions of this topic, and they all have a consistent view of this partition map.
So is that what you're saying here? Is like we have a controller partition that's replicated across different brokers, so they all get to see what's going on. So every actions or every items or every partitions added, they all get to add it into this controller. Is that what's going on?
Yeah. So it's like analogous to what Kafka has in Zookeeper, right? So they have a kind of a metadata store that is set apart.
Right.
But in Redpanda, it's, just simpler to deploy. All nodes in the cluster, they're just in one Raft group, sharing this controller partition. And one of the cluster nodes is actually like a leader of this partition, right? So Raft is a consensus algorithm where you have a leader. So one of these nodes will become a leader, and it's called the controller leader. And it has special functions in the Redpanda cluster. So this is the node that will orchestrate all this partition balancing. So so what happens is all Redpanda nodes who have this partition, they elect a leader, and when or if one of the node crashes or has some problem, right, the leader will just transfer to another node, and this node will like pick up where the previous one left. So like for example, partition balancing duties will be transferred to this node.
Can you dive a little bit deeper into the Raft? Because I know Raft is a consensus. Okay, we've a question here from Fami actually. How does the 3 controller gets in sync? I think that brings up the Raft question as well, right? Like, can you explain a little bit about it?
Oh yeah. So like if you read the scientific literature about consensus algorithms, it's all very abstract. Like there are 3 proposers, proposing something and then trying to agree on this. But what distinguishes Raft, it's that it's a little bit more down to earth, and I guess that's why it's popular. So what Raft does, it maintains a replicated log. So this is a data structure, which is quite similar to like what a partition is, right? So in a partition, you have messages that you append to the end of the partition, and which are then get replicated to other replicas. So this is what a Kafka partition is, and this is what Raft maintains. Raft algorithm maintains. So it's kind of very natural that you can use the Raft algorithm for maintaining this replicated log data structure across several replicas.
So once we have all these separate replicas, I think like how do they get replicated? I think
so what happens is that we have this leader, and it actually is responsible for appending new data to this replicated log. So for example, we can again use this example of adding a topic, right? When you add a topic, you send a message to the controller leader, and it will then do some checks on its own if it's possible to create a topic or whatever, and then it will append this message to its own log, and then we'll send RPC calls to other nodes, like pushing this data to other nodes, and they will receive this RPC and append to their own logs, and this way they will maintain the log that is consistent across replicas. And Raft algorithm, it's a bit complicated, but it ensures that there is a point in this log where you can be sure that like if you are in the majority of replicas, if you can hear from them, this means that up to this point, all replicas will maintain the same log. So a little bit at the end can be different across nodes, right? So for example, this command hasn't yet been replicated to other nodes, but this point of agreement will move just farther and farther along the log.
So the controller will be kind of giving our PCs or command to the majority of the brokers in the raft consensus ring, right? So you kind of just have to, so that's majority. You don't have to get every single one of them, right? That's isn't that the beauty of raft, isn't it? Like,
oh yeah, it's actually quite nice that you don't have to get to every broker, every other broker, because you can have problems with tail latency because some of the brokers can be slow, right? And this will bring tail latency to your calls. But yeah, with Raft, it's not a problem. You just need the responses from a quorum.
So can you tell us a little bit more about, how when you do self-healings or, auto rebalancing, there's so many different factors that needs to be factored in, like when you do like rebalancing, because, different brokers have different situations. So how do you determine that? What's going on? Like, how does the leader select and then, do all this replication? Does it do anything, or how does it done? Can you tell us a little bit about what's behind the scene?
Oh yeah, so we actually, to do this continuous balancing, we need a lot of information about other nodes apart from this partition map, right? And also there is a list of brokers in the cluster as well, and it also is maintained in the controller log. And so what else do we need? We need information about disk usage. So if we have a node that is overflowing, like it's using, I don't know, 80% of its disk, it will send this information back to the controller. Also, we need information about node health. So it's a bit of a tricky subject because, like a node can be reachable from a perspective of one node and not reachable from a perspective of another one. And yeah, it's always tricky, but we always use the perspective of the controller reader. So if this node is can reach like a majority of the nodes in the cluster, probably it has a good enough view of which node is healthy and which is down or whatever. So this is actually like a separate thing that the nodes will periodically exchange called health reports. And yeah, it contains this, ephemeral information like disk usage or yeah, if it's down or not. So this is not part of the controller partition, and it is just ephemeral, like when a node will come up, it will announce itself and send its information to the leader.
I think that's pretty smart, like coming from because I always thought like, when the leader is trying to find its where to replicate things, it will ask a node, for its health. But it feels like we're doing that separately, so we don't have to always ask the same questions. I think that saves on the traffics going through with RPCs. So I learned something today, right? It's pretty cool. I mean, so that means like we're pretty efficient on getting the node information, health information separately. But there's a questions from Fami about syncing the whole partition every time, or is it syncing the segment within the partition? Can you kind of quickly tell us, like, so for the partition replication, does it synchronize the whole partition? So does it wait for the whole partition to fill, or does it just synchronize like partial partition, like when the data arrives? Can you tell us a little bit about it?
Yeah, first I need to clarify that this is a separate partition from data partitions, right? That are Kafka partitions that hold user data. So this is a small partition that holds this metadata updates. And yeah, so this is a bit of, a storage side question about a bit more low level. So the way the log the logs in Redpanda are organized like both for data partitions and for system partitions is in segments. That's right. So if you like, if you are curious like me, you would go into Redpanda Data directory and you will find all these partitions there. And each partition is a log consisting of several segment files. So segment file is, I don't know.
It gets rolled, right? Every segment gets rolled.
What's our default? I guess 256 megabytes, something like this. And yeah, after it's full, it will get rolled.
Yeah.
And yeah, it will be just another file. But yeah, actually, to make sure that data is safe on disk, especially for controller partition, it's very important because yeah, otherwise Redpanda will just forget that there are some partitions there and will lose it. So every time there is a write to it, there is an fsync as well, right? To make sure data is durable on disk. And yeah, but we kind of do it in parallel. So we send to other nodes and in parallel do fsync on the leader. And this will, this ensures that we're kind of doing it concurrently. So it's not that big of a latency burden.
All right. So, okay. So there is another questions coming from Tammy about the controller leader directs repartitioning as well. So if you're doing repartitioning, all that, does the controller kind of do the repartitioning, or does it just do the replication or doing the rebalancing? Does it do anything, include like doing the repartitioning part? So I guess it's more like the data storage.
Yeah, it's actually hard for me to understand what repartitioning is. Because yeah, it could be rebalancing, right? But it also could be a process when you have a topic with some amount of partitions and you write data to a topic with, I don't know, bigger number of partitions. Yeah, that's what I would call repartitioning. Yeah, but right.
So he says rebalancing. All right. So rebalancing.
With respect to rebalancing, yeah, I would say like as a computer, like as a physical node, yes, it's doing rebalancing. But if we want to sound fancy, we can say that it is maintaining a lease on, you know, partition balancing duties, right? And it will, so there is a process in each Redpanda node and that is trying to grab this lease. And when the controller leadership comes to this node, the process on this node will start and assume that it is responsible for partition balancing. And actually, like, because to do actual balancing, it has to append entries to this controller log. It will make sure that there cannot be like two processes doing it, right? So a leader will, you know, assess the situation, say, okay, I need to move some partitions here, some partitions there. And if this happens, that it will lose leadership in the process of, you know, this planning phase, right? It will just fail to append its commands to the controller log. So this kind of ensures that there's only one process in the whole cluster doing this rebalancing.
All right. So I love the questions. Keep them coming. I think they're very good because it helps me understand that too. So there's another question coming in, says, do we, from Fami as well, could we have a number of replicas more than the number of brokers?
No, that's forbidden.
Can we have more replicas than more than the number of brokers? So we can have like replicas of 4 brokers.
For a replica, it's for each replica, there is a hard constraint that it should be on a separate node. So you can't have 2 replicas on the same node. And so, yeah, by, you know, basic exclusion principle, this means that if you have more replicas than number of nodes, you can't satisfy this constraint. So yeah, that's forbidden.
Yeah, I guess I like that question because but the thing is, when you think about replicas, right? Like, why would you replicate things on the same node when it could all die at the same time, right? Because that's the whole purpose of like replicating things, to make sure that they are like, saved somewhere. So so for me, I think it's maybe it shouldn't be but it could have two storages as well. Yeah, I mean, you're right, but how do you know it's writing to that storage, right? So I'm just kind of curious, like, but that's a very cool thought as well. So is there anything you want to add in terms of like how everything works for rebalancing and self-healing? How do we kick it? So when does it kick starts, right? So that kind of curious. I know how everything gets into the controllers, and controllers just make sure that the rebalancing is working, all just one process working on the rebalancing stuff, right? So how does it know when to start? Like, is there any mechanism that we looked at? How does it start? Can you kind of tell us a little bit about it?
Oh yeah, so this is like we starting from higher up and moving a bit down,
right?
To low level stuff. So yeah, it's a great question. And so when we have this information about node liveness, right, and node disk usages, it's actually checking it periodically. So there is like some period, which is I think 30 seconds by default. And it also can be, kickstarted by some other events, such as, node decommissioning and stuff like this, so that you don't have to wait like the full quantum of this period. And yeah, if the rebalancing process, so it does its magic, it kind of checks every constraint that it has. And if it
what are the constraints? Tell me. Like, I'm curious.
Yeah, if you go, one of them I already told you, like you can't have replicas on two replicas on one node. But also you can't have replicas on decommissioned nodes. So like in the process of decommissioning, you mark this node that it's decommissioned, and this means two things. First is that you can't add new partitions to this node, and second, it means that old partitions shouldn't be there, right? So this is a constraint that, and also like if you're planning some partition moves for other purposes, right? This moved replicas that you're trying to find a place for, right? They shouldn't go into decommissioned node as well. So this is an example of a constraint, and there are like quite a bit more, which are kind of, we can think of two ways to view a constraint, right? One is that it is a constraint on placement. So when you're trying to find a place for a replica and you kind of look through the list of nodes and say, okay, this node is doesn't fit according to this constraint, this node doesn't fit according to that constraint, and all of that. And another way to look at it is that you have existing replicas, right? And something can change, and these partition replicas can start violating the constraint. So for example, a node will go down and will have a constraint that a partition replicas shouldn't be on that down node, right? So this means that we should move replicas away from this node. So this is kind of a trigger for moving partitions. And yeah, after it plans all its moves and it tries to not be too overwhelming, like not do everything in one go, because it can be quite taxing on the cluster. It will submit this commands to the controller log that we discussed earlier, and This means that all brokers will update their partition map that they maintain, right? This picture that we have. And then there is, I guess you could call it a reconciliation pattern, right? So there will be a discrepancy between what's in the partition map and what's actually on the nodes, right? So some nodes will have replicas that shouldn't be there, and other nodes will won't have replicas that they should have according to this map. So nodes will start working to reconcile what's actually there to this partition map. And so this will kickstart the actual movements. And yeah, it's also a very interesting topic because
so when it kickstart the movement, what's
Yeah.
actually happening? Because I assume there's going to be a large amount of data if we have a lot of partition that needs to be moved. Data are starting to do a bunch of RPCs in between brokers. I assume the network's going to get busy, the disk IO is going to get busy and all that. So how do we constrain everything so we're not taking the entire like capacity of the hardware? Do we have any constraints on that, or do we just kind of let it go? Or is there any like configurations that we can do to kind of do that? Is there kind of just, how do we do that there?
Oh yeah, there is. So this is actually another job of partition leaders, right? So when they notice that the set of replicas that they maintain is different from what's in this global map, they will start the process of what we call reconfiguration. And yeah, it's a bit of a bad term, but it's it's taken from the RAF paper, or from, I would say, RAF dissertation, because
All right, if it's not a paper, we'll take it, right? It's a paper thing.
yeah,
Fine.
it's a paper, so it must be correct. But yeah, I would say like the reconfiguration section is a bit light on the details, so we had to fill a lot of it ourselves. But yeah, it's actually pretty cool because it allows the leader. So this is yeah, what we call moving a partition, and it kind of brings you a picture of, you know, you take a partition from one place and you move it to another. But actually what happens is that the leader will bring up the replica in the destination place, and then after everything is okay, the source node will just delete the replica. And this actually means that you can move partitions from nodes that are down, right? Because yeah, if you were just moving from one place to another and the source place doesn't exist, you couldn't do it. But right, this is the leader doing it. It will what we call recover a new replica on a destination node. And what's a bit of magic, I would say, is that through the whole of this process, you still can read and write the partition just as if nothing happened, nothing is happening. So that's pretty cool. And
how do we do that? Because I thought leader is kind of in charge of, you know, replicating things over to the destination, but then we also have producers trying to write into the leader partition, and then we also have consumers that's going to read from the leader as well, right? So unless I'm doing like, you know, the other thing where consumers are listening from the replicated partition, but I don't think most people do it. So how do we do that? Like, can you tell us a little bit, like, how do we make sure that everything can continuously working while we're doing the replication?
Yeah, actually, the producers will always contact the leader to produce. So the, how should I put it? Yeah, all updates flow through the leader, and usually all reads flow through the leader as well. But yeah, in the new Redpanda release, we have this follower fetching feature that actually allows you to consume from the follower, from the replica. But yeah, of course, it doesn't include replicas that are still not up to date, which are like the moving, movement targets. This is what is in Raft paper, and we call it learners. So it's like a node that hasn't yet learned the full log. So it's still learning, and when it is finished learning, recovering, right, it will become the full-fledged member of this Raft group. And yeah, like in theory, it shouldn't be disruptive to the produce and consume process, but of course, like it's an additional burden on the system resources, because the leader will just, if you don't apply any resource limits, the leader will just read the partition at full speed and blast it through the network to the recovering replica. And yeah, so this could be disruptive for client traffic, which is very important to maintain all this nice latencies that we have. So yeah, we have rate limit on this traffic. So it's by default like 100 megabytes per second. But yeah, I guess if you have a better network, you can tune it up.
I think that's a great point, because I think, if I'm maintaining a Redpanda cluster, if I see the tail 99 latency is not up to my standard, I could then quickly check if my node is doing some kind of rebalancing, and that could be some kind of problem with my existing node. So that kind of puts all the puzzles together, like I think it helps me with that. So I can kind of see, all right, if there's something goes wrong, something's taking up that traffic, this might be something to do with like doing the replications and like the with the rebalancing stuff, right? So I have a question from Fami, but I think your question related to pushing data to S3 is more to do with our tier storage. So what I'll do, I will try to invite our tier storage experts here next time, or maybe in a couple of months' time. So he will be able to answer your question. I think that's more of a question for the tier storage team. So hold that thought for a couple of weeks.
I can answer that briefly.
Oh, you want to answer it? Okay, perfect.
Sure.
Because I thought you wanted.
Yeah, I did actually I wrote a bit of code for the initial tiered storage implementation. Okay,
perfect then.
Yeah.
Go ahead. So he basically, so what Fami wants to know is how do we replicate, how do we balance the replicas between our remote storage and our local storage?
Yeah, so it's kind of independent, right? So for a single partition that is using tiered storage, you have like a bit of a local part, right? And a part that is replicated to the tiered storage, and it can, go into the past for quite a while. And what's happening in this partition moves is that this local part is moved, right? And the part that is replicated to the S3 or archived into the S3, it stays there. So if the partition leader changes, of course, it will also need to have a connection to S3 to continue uploading the data, and it will just continue from this point where the previous leader left. So it's kind of independent, right? There is this local part that is moved across brokers, and there is an S3 part which is kind of shared across all brokers because it's an S3 after all, right? And Yeah, it's another responsibility of the partition leader to upload this data into S3. And yeah, if the leader changes, it will just continue from where the previous one left and continue uploading.
And Tammy has a question about, is there a separate partition leader for each partition? And is it different than the controller leader?
Yeah, good question. Each partition has a separate leader, and it's another fascinating topic, but different from this one is leadership balancing. Because yeah, as I already told you, leaders for ordinary data partitions or Kafka partitions, they also have a lot of responsibilities, right? For example, uploading to S3, serving produce requests, so serving consume requests. So it's also important to balance them evenly across the cluster. And yeah, that's another component that does it, called leader balancer. But yeah, I guess we won't talk about it today.
Yeah, we'll invite the leadership balancer engineer next time if you want to. We can talk about it. How do we balance the leaders and do all that? But I think we have a lot to dive into that as well. So, like, what's the difference between a decommissioned node and a sudden crash of node? Is there a difference when you talk about rebalancing? Is it more graceful when we do decommission, or does it really matter for us when we do replication, rebalancings, and just to try to self-heal from the situation?
Yeah, I would say with regards to partition movement, there is almost no differences. So like after a while, a node that was down for some period of time, yeah, it will, like the continuous balancer will notice it and start moving partitions away. And this is also what it does for the decommissioning node. But the difference is that at the end of this process, when there are no partition replicas on this node, what happens then? In case of a node that just crashed, that is dead, it can come back online, and it will still be part of the cluster. So we could, move some more partitions to it, some other partitions to it. So you won't have to, start from scratch.
What happens if there's a network glitch and suddenly the node went offline and came back up right away? Does it automatically cancel the rebalancing, or does it continue to do that until it finds the latest status of the cluster and then redo the calculations? What's going to happen there?
Yeah, so it's a bit of empirical thing, right? So this timeout is, I think, by default 15 minutes. So it's much more than what a sudden network glitch could be. But of course, like a node can come back in the process of this moving partitions away from it. And when it will come back, of course, we will stop this process. It won't continue. But yeah, this is actually something that we need to improve because we won't bring these partitions back that we moved away. So yeah, this is a future area for improvement.
Speaking of future,
yeah,
I know we've done a bunch of updates for this new release. Can you tell us a little bit about that?
Yeah, so in the latest version, 23.2, there are quite a few updates related to balancing. So one of them is that it should be quite a bit faster. So
why is that?
Yeah, it's quite a bit more aggressive, I would say, in scheduling these moves. So previously it was, it scheduled a bunch of moves and then waited for them to finish. Then it scheduled another batch of moves and waited for it to finish. And that could be quite slow to, wait for this last partition to finish its moves. And now it just maintains the, you know, constant number of partitions in flights in flight. So it's like it's 50 partitions by default, and yeah, it will schedule some moves. Some of them will finish. It will schedule some more, and yeah, this way it should be much faster. And also we made some improvements to this throttling or rate limiting, right? Because in previous versions it was a bit so the partitioning of yeah, it's a bit loaded word, right? So yeah, let me just say that now a single partition movement can use a full bandwidth of a node. So if you have like a single partition moving partition movement, then it can use the whole 100 megabyte per second. And in previous versions, that's not true. So like individual movements, if they're like last movements in the batch, right, they just became much faster.
I see.
So yeah, that's one area of improvements. Another one is that is related actually to decommissioning. So yeah, I wanted to just finish what the difference between a dead node and decommissioning node is. And the difference is that after decommissioning, the node will no longer be part of the cluster, right? So if it comes back, it won't be able to join. And if you want to reuse it, you'll have to, you know, erase the data directory, give it a new node ID, or have Redpanda give it a new node ID. So it's like a new node for all purposes. So yeah, that's the difference. And yeah, the decommissioning process also got improved because in previous versions of Redpanda, there's a bit of a divide, right? When we are moving, for example, partitions away from a dead node, we're taking into account node health, right? In a couple of words. So if the node is alive, if it has enough disk space for, you know, for hosting this partition that we're trying to move there. And in previous version, the decommissioning process like was a bit less smart, and it wasn't using all this information. So for example, you could end up with a movement of partition from a decommissioning node that, you know, the controller will just schedule it on a dead node. And of course, it's not going to finish. So you could get the decommissioning process stuck. But yeah, in your version, it's smarter. So it will take this into account. It will ensure that there is enough space, that the node is actually alive. And yeah, so that's another area. Yeah, there are a few others, but they're like smaller in.
Right. I guess the last one is very, very smart, right? Because then you're not stuck into like it waits forever to actually decommission a node or a broker, and then you're kind of smart enough to kind of find the strongest, well, the healthiest broker to be like. Is that the best word to describe it?
Yeah. Actually, like another funny thing that could happen is that a node could go down in the middle of the movement. And yeah, that's pretty unfortunate, but we still have to handle it. Yeah, for this, there is also a possibility to cancel a node movement. So,
yeah, you know,
so
you can never tell what's going to happen in the cloud, right? They could suddenly just die and then you're like stuck there forever, right? So that's really smart. I think we're almost at the end of the hour because this was like a 45-minute session and we already like used up too much of our time. But you know what? Alexey, do you think that Tammy and Fami should all get a t-shirt? I think they should, right? Because they all ask like awesome questions, and I think we should reach out to them and give them t-shirts, right? What do you think?
Oh yeah, sounds good.
Awesome. Right, so we'll reach out to you, and then you'll get your t-shirts. Thank you for asking all these great questions. And Alexey, anything you want to add before we end the session today?
No, I guess, yeah, I could talk for a long time, but yeah, we can finish now.
See, I told you we need you in another couple of weeks, not months. All right, so it's great to have you all here. Thank you very much. And Alexey, we'll probably see you in a couple of weeks. But all right, thank you all.